police.
Okay, this is the Taser International X26 Taser.
The taser works by sending a pulse of electricity across a pair of metal prongs, which disrupt nerve and muscle function.
It will deliver 50,000 volts downrange to the target individual, causing the muscles to cramp up, and therefore the person should not be able to fight us anymore, and we'll be able to take them into custody. Taser, taser, taser.
With a maximum range of 10 meters, it uses a dart that can penetrate 2 inches of clothing and is even effective on someone wearing body armor.
We don't have to worry about, chemicals in the eyes. We don't have to worry about the bruising from the impact munitions. So it's been a godsend for us.
Down, 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 down.
Thanks to this new generation of non-lethal weapons, the police have some formidable new tools in their fight against armed criminals.
Put it down! Drop the pipe!
Behind the ordinary objects which surround us in our day-to-day lives lies something extraordinary. Incredible stories of ingenious solutions to problems most of us never knew existed. So what mysteries are concealed in everyday things we take for granted? Recycling, plasma TVs, fireworks, railway tracks, and ink cartridges. 5 ordinary things, 5 extraordinary stories, now revealed as we go behind the scenes, inside the machines to find out, how do they do it? Ever wondered what happens to old aeroplanes? Bizarre as it may seem, they're turned into mobile phones. That's right, a chunk of these massive old warplanes will soon be a designer slimline cell phone gently vibrating in someone's coat pocket. So how do they do it? Welcome to the Davis-Monthan Air Force Base near Tucson, Arizona. Davis-Monthan is a jet plane junkyard for the US Air Force. At Davis, you can find hundreds of old warplanes from F-4 Phantoms to B-52 bombers, all quietly broiling in the desert sun. This is where old planes come to die. But it's also where they get resurrected into something new. The Lockheed C-141 Starlifter is a troop and supply carrier, once the pride of the Air Mobility Command. After more than 40 years of military service, the Starlifter looks like a tired old warhorse. But to salvage worker Ramon Martinez, the old Starlifter has just what you need to make new high-tech mobile phones. Tons of metal sheeting, miles of wiring, thousands of electrical components. Martinez has already removed much of the plane's interior. All that remains is the shell. In one piece, it's too big for the recycling machine. But Martinez is about to fix that. With Martinez at the controls, a massive excavator comes to life. It's a machine that's normally used to erect buildings and bridges, but today, it's a plain killer. Like a voracious beast, the cat advances on the Starlifter. What follows is not for the faint-hearted. First, Martinez rips off the pods that held the engines. Then, he hacks off the wings, one by one. After that, the relentless jaws of the cat close upon the tail section. Finally comes the fatal blow. Like a predator tearing at its prey, the cat rips out the innards of the stricken Starlifter. It's not pretty. To some, it might seem gruesome, but it's effective. In just 40 minutes, no section of the plane remains unscathed. What's left are not exactly bite-sized chunks, but they're small enough to be carried to the next stage in the plane's transformation. Half a mile away, the Starlifter faces more chomping from more metal mashers. But there's still nothing here that looks like it could be turned into a mobile phone. Time to pay a visit to the Hammerhead Mill. This is an old aeroplane's worst nightmare, where a B-52 finally meets its match. Bits of plane are fed into a rolling mill. Steel spikes mash them up into unrecognisably small pieces. And this is what's left. Thousands of small scraps on a conveyor. But now comes the tricky bit. There are all kinds of components here, made of steel, aluminium, even plastic. Somehow it needs sorting through. And this is how they do it. At the end of the conveyor, a powerful magnet literally sucks iron and steel into a separate hopper, allowing aluminium and plastic to drop directly onto a second conveyor. A manual trawl for unwanted items, another round of grinding and mashing, and what you're left with is the stuff mobile phone circuit boards are made of. It seems hard to believe that redundant bombers and jet fighters find a new life inside your coat pocket. But they're not just in your phone. Believe it or not, the inside of your TV, or computer, or car radio is just as likely to be made up of old military hardware. 5 ordinary objects, 5 extraordinary stories. Coming up, these new TVs create amazing pictures on a wafer-thin screen. But did you know they work using a kind of cosmic gas? The secret behind plasma TVs. Next, on How Do They Do It? We live in an age defined by TV. It entertains us, it informs us, it is our window onto the world. But a revolution is transforming television. Not what's on it, but what's in it. Welcome to the Plasma TV. To make plasma television super thin, you need to harness a fundamental cosmic force. The glass screen is filled with gas, but not just any gas. It's the gas that makes the northern lights flicker in the upper reaches of the Earth's atmosphere. It's the gas that lights the sky with lightning rods hotter than the surface of the sun, and it's called plasma. It's the weird substance behind these natural wonders which is the secret ingredient in ultra-thin TVs. So, how do they do it? It's a rainy day in Miyazaki, South Japan. In this factory, Hitachi make 500,000 plasma TVs every year. This may look like a normal television screen, but look closer and you'll see not one but 2 glass plates clamped together. It's what happens in between that is the secret to the production of the ultra-thin plasma television. Between the plates lies a matrix of 1 million individual and minute cells, each one a fraction of an inch tall. Across the top and bottom layers of the glass are hundreds of thin electrodes crisscrossing one another. Their job is to create an electric environment that charges a mix of inert gases that will soon fill up those cells. The gases are called neon and xenon. Once charged with electricity, they create plasma. Most people imagine there are only 3 states of matter: liquid, gas and solid. But there's a 4th, plasma. And believe it or not, it makes up nearly all the visible matter in our universe. By charging certain gases with electricity, it's possible to create plasma. And this plasma transmits light. So how do you recreate the northern lights inside a TV screen? First of all, fill it with neon and xenon. This tiny glass tube is fitted to the back of the screen by a robotic welding device. Using the tube, air will be sucked out and a gas cocktail will be pumped in. A short trip to an airtight section of the factory where the gas is stored. This is where chemistry meets engineering. The screens emerging from the chamber are full of gas, but there's one problem. charged neon and xenon only generate ultraviolet light, invisible to the human eye. The solution? Another clever bit of chemistry. Each cell has been coated alternately with a red, green and blue chemical, called a phosphor. So each pair of glass plates now contains a matrix of microscopic electrical wires and a honeycomb of minute cells, each filled with neon and xenon, and now delicately coated in various kinds of phosphorus chemicals. All that's needed to make the plasma do its stuff is the flick of a switch. This technician is creating a kind of electric storm right in front of our eyes. As an electrical charge surges around the components, the screens burst into life, and a plasma TV is born. This explosion of coloured light shows the phosphors and the plasma are working. Now it's the job of the electrical circuits to combine the right cells to produce the right colours.
Plasma can identify 1 million colours. That's more colours than the human eye can recognise. I think plasma is a great technology.
But a TV that runs on gas with a little help from electricity poses peculiar problems. In a normal TV, you don't want faulty electrical circuits. In a plasma TV, you don't want a gas leak. So the screens visit the aging room. In here, hundreds of plasma screens are switched on and left for hours to make sure the chemicals are contained and stable. The plasma screen is working, but there are no pictures yet. There are no tuners, no receivers, no aerials. There's still a plasma TV to be built. Generating sound and vision involves thousands of individual components. Stored on reels of plastic, they're fired at high speed onto circuit boards. High-pressure plastic injection machines produce the various casings for the different sizes of plasma TVs made here. Then everything is brought together on the production line. Circuit boards which control the signal, the power, formats and tuners are all placed on the inner back wall of the TV. But right now the screen has a poor contrast ratio, giving off a kind of milky grey light. So another screen is added to increase the contrast. Then everything is checked again. Colour bars make sure each TV is producing the correct colours, whites and blacks, rather than muddy greys. Test patterns, formats and functions all need to be assessed. These guys at least get to watch the front of a TV screen. Spare a thought for Satoshi Maruono. It may sound like robotic bedlam, but to Satoshi's trained ear, the chirps and squeaks tell him if the TV's working as it should. And some tests involve a highly technical process. He's listening for loose screws. Satoshi sees the back of hundreds of TVs every day, and he'd much rather be watching the front.
I love TVs so much that I make them for a living. I don't have a plasma TV myself yet, but I do dream about getting one.
After packing and boxing, a few TVs are chosen for one last bone-shaking quality check. Every now and again, a television is taken off the line and subjected to a spell in the vibration chamber. A metal floor plate shakes the TV to make sure everything is screwed together properly and that there are no loose parts. When you open your TV's packaging, everything should have been shaken, but not stirred. As the workday comes to a close, the TV sets are loaded onto trucks to be shipped around the world. Box upon box of cosmic plasma destined for your living room. The plasma technology behind your flat-screen TV is now also used in manned spaceflight, as a propellant in spacecraft thrusters. Back in the factory in Japan, the day shift is over and the workers have gone, leaving the plasma sets switched on to dream quietly of the northern lights in glorious Technicolor. 5 ordinary objects, 5 extraordinary stories. Sunset over New York. It's July the 4th, one of the biggest dates in America's calendar. Independence Day. Excitement fills the air. New Yorkers make their way to the dockside for a front row seat at one of the biggest shows on Earth. The most gigantic firework display.
All over the world, people love fireworks. Nobody likes them more than the people in New York. We're convinced of that.
For days, a team from Macy's department store has been coordinating a massive operation involving engineers, TV crews, police, and city and government officials.
We deal with so many city agencies and so many people that work for those agencies, outside vendors, volunteers. All told, there's about 5,000 people that need to come together and be on the same page for this.
A lot of effort for one of the biggest shows in the world. The vision of this man, firework designer Gary Souza.
For me, the first few aerial shells that go in the sky, I am just totally thrilled. To me, that's the best moment in the whole show, because then I know that things are going to work.
Souza knows he's only going to have one chance to get this right. By definition, you can't rehearse a fireworks show.
Basically, you get one shot at it, and if it doesn't work, it basically sucks.
The Macy's firework display will be one of the biggest and best ever. Yet, no matter how high-tech it all seems, even the most spectacular firework is the product of a very ancient technology. So, how do they do it? The story starts half a world away. In the Chinese city of Liuyong, they know all there is to know about fireworks. Because fireworks is about all this town makes. Indeed, fireworks are so central to the city's way of life that they've even put up a statue to honor them. One of Liuyong's biggest employers is Black Cat. The company manufactures all sorts of fireworks which produce the most exotic effects. But for all the modern packaging, the fireworks we use today remain the products of ancient techniques developed by the Chinese 2,000 years ago, here in the hills surrounding Liuyong. They still make fireworks in these hills. It's too dangerous to do it anywhere else. And this is why. Black powder, the Chinese call it, a blend of charcoal, sulfur, and potassium nitrate. By themselves, each of these chemicals is harmless enough. But once they've been mixed, look out. The powder is mixed by day, and it's tested by night. Black powder was invented here 2,000 years ago. Put a match to it, and it does this. The potassium nitrate in the mix acts as an oxidizer. In other words, when heated, it creates oxygen to make the other ingredients burn fiercely. But the ancient Chinese alchemists soon discovered something else interesting about black powder. When it's packed into a confined space, like a tube, kaboom. Pyrotechnicians call this effect the bursting charge. The ancients also learned that if you make a hole in the bottom of a firecracker, you can direct the force of detonation downwards. You get what is now called a lifting charge. And that's what makes a firework fly. In the light of day, manufacturing continues. But now we come to the most astonishing secret ingredient essential to making a firework. How do they turn simple rockets into amazing fireworks that perform all kinds of fancy tricks? How do they create the cascades, the clusters, the rings, the starbursts? The secret ingredient is rice. These pellets are filled with gunpowder. The Chinese call them pearls, and they're made from dried rice husks which have been coated with a slow-burning mix of powder and glue. The pearls stop the gunpowder from exploding all at once. To get multiple effects, pack the pearls into spheres called shells. To get different colours, add different kinds of mineral salts. Strontium for red, barium for green. To get sparkle, add flakes of aluminium. Link the shells to the main charge by time delay fuses. Light the rocket, and you'll set off a spectacular chain reaction. each wave of rice pellets ignited by the detonation of the previous wave. No matter how big or complex, all fireworks are based on this simple chain reaction effect. All you have to do is use more rice and different kinds of shell. July 4th, Manhattan. As darkness falls, anticipation builds. It's showtime. Back at the control center, the countdown begins. In a few short moments, the team here will unleash a barrage of high explosives across the city skyline. Quite suddenly, it begins. At a rate of 1,000 shells a minute, the team launches a staggering 40,000 tons of high explosive into the sky. It's a truly awesome spectacle. The technology may be 2,000 years old, but there's still nothing to beat a firework display.
I love the fireworks the best. There's just something magical about them. This was the event that caused me to want to do events for the rest of my life.
An amazing sight, and it all comes down to a bit of chemistry, a lot of rice, and a simple chain reaction. On July the 4th, thanks to Gary Souza and his team, and an age-old technology from China, New York City celebrates American independence with a bang. 5 ordinary objects, 5 extraordinary stories. Coming up, the rail track. It's the secret behind rapid mass transit. Next, on How Do They Do It? They call it a cathedral to industry. But it feels like the gateway to hell. It's big, it's hot, it's noisy, and makes something many of us use every day without even thinking. Rail tracks. But these are no ordinary tracks. These are the longest railway tracks ever made. At 120 meters apiece, these tracks are designed to serve Europe's high-speed rail network. High-speed rail networks carry trains at phenomenal speeds, around 350 kilometers per hour. That's equivalent to a Formula One racing car on full throttle. Normal tracks can't cope with the stresses and strains high-speed trains impose. Too many welded joints between sections of track, too many sharp bends. To make the journey smooth and safe, you need fewer welds and gentler curves. And that means making single sections of track the length of a football field. So, how do they do it? The story starts here, deep in the heart of the Austrian Alps. The gingerbread houses and snow-capped mountains may seem an unlikely location for heavy industry. But it's this spot that Austrian rail giant First Alpina has chosen to call home. The tracks are born in a furnace. Steel ingots cooked at a searing temperature of 1,400 degrees centigrade. In this heat, impurities in the steel float to the surface and can be cleaned off. But how do you clean a red-hot chunk of steel? As they emerge from the furnace, the fledgling tracks face a violent baptism. A cleansing, a dousing in a high-speed jet of water. The process is called descaling. The steel is so hot, the water literally explodes on contact. Descaling is spectacular. It's also practical. The explosive force has a scouring effect on the ingot surface. It's steam cleaning taken to the extreme. At this point, the cleaned ingots are featureless steel planks. Turning them into rail tracks requires some formidable hardware, called rollers. In an adjacent workshop, you can see the tracks taking shape. The rollers are giant steel cylinders carefully tooled with grooves that will mould the track head and stretch the steel to that final 120-metre length. The giant tracks move back and forth through the rollers on the floor of the plant no less than 16 times. With one new red-hot ingot hitting the floor every 5 minutes, track rolling involves a skillful bit of choreography. And this is where the dance master sits. A control cabin looking straight down onto tons of red-hot steel. Get the timing wrong and you'd end up with one heck of a pile-up. Tons of red-hot steel bent hopelessly out of shape.
If you get out of step with the rail tracks, either moving through the system or coming back, then yes, a collision is possible.
To avoid pile-ups, the controller sends half-finished tracks up a ramp to one side, allowing the next track to enter the system. Once milled to the correct shape, tracks face another trial by fire. A giant circular saw cuts them to precise lengths according to a railway's needs. The tracks are now the right length and shape, but there's a problem. The track head is too soft. A typical high-speed passenger train has a dozen carriages. Each carriage weighs 65 tons and has 8 wheels. When fully loaded, this means up to 11 tons are pressing down onto the track through each of the train's wheels. It's a force equivalent to the weight of Egypt's Great Pyramid pressing down on an area the size of a small backyard.
When you're looking to the forces which are running, which are brought onto rail day by day, these are tremendous forces.
This tremendous friction created by all that weight pressing down on the wheels and the track would soon wear out both of them. First Alpina has come up with an answer. Harden the rail track head. Soaking the cooling rail track in a kind of liquid plastic called polymer knits steel molecules together in a far denser pattern than that produced by cooling in the open air. The effect of hardening the track head is to reduce the contact between track and wheel.
The contact areas of steel wheels of a train in combination with the runaway with the head surface of a rail are very, very small. Only a couple of square millimeters per wheel.
The result? The wheels glide over the track head surface, and that means less friction and less wear. Back in the plant, the tracks get a final milling to make sure they're absolutely straight. And then comes the acid test. The tracks are long, they're straight, they're hard, but they're going to have to face 25 years of brutal use. So, are they safe? It's Christian's job to find out. The machines that Christian tends have one task: to spot the kind of imperfections in the steel that could cause a train crash.
In the inspection area, we check the tracks for both surface and interior faults.
At a speed of 1.5 meters per second, each new track is fed through a series of 4 different automatic inspections. Light scans check for surface imperfections. Magnets check for invisible faults in the steel. and ultrasound is used to check the inside of the track. The computer has spotted something. It's a tiny blemish in the track. Although it's small, even the slightest flaw in the composition of the steel can cause fractures or premature fatigue deep inside the track. If anything shows up, the track is diverted to a manual inspection area. The inspection must be thorough. Every scratch is closely examined. Sometimes it's only a surface abrasion, but if it isn't, the track is rejected. The folks at First Alpina take track safety very seriously.
Passengers' lives depend on these rails, and that's why inspecting them is so important.
Millions of people rely on railways worldwide. In Europe, rail travel remains one of the safest forms of transport, thanks largely to the precision engineering behind the high-speed rail track. 5 ordinary objects, 5 extraordinary stories. You're looking at a high-tech miracle, an incredible event, so familiar to most of us, we don't give it a second thought. This is a close-up view of a computer printer cartridge delivering ink to the page. These droplets occupy a tiny space, yet printer cartridges can fire millions of them a second to form extraordinarily sharp color images. So, how do they do it? Hewlett-Packard is the world's largest computer printer manufacturer. The company plant lies just south of the US city of Portland, Oregon. 800 people work here around the clock to supply cartridges for 20 million printers worldwide. Disassembled, the cartridge looks simple enough. It's made up of 3 main components: the ink held in this reservoir, the firing chamber, and a small plate peppered with tiny nozzles. Together, as a microscope reveals, these components produce something amazing. Images and words delivered as a distinct series of tiny dots. Hundreds to the square inch, many thousands to the page. To do its work, the cartridge must exercise a very precise control over one thing. A droplet of ink so small, it could sit on the tip of a human hair. Computer ink is a highly engineered liquid, 80% water, 20% a blend of solvents, pigments, and a kind of liquid plastic called polymer. The balance of ingredients is crucial. Here at the ink lab, technician Melinda Pride checks for color bleed. It's called the egg yolk test. Put a blob of yellow ink into a dish and add a drop of black. The black should hold its shape, even when the dish is agitated. After checking for color fastness, technicians then check for color permanence with a relentless ink-killing machine which shows no emotion and knows no mercy: the faderator. Using a battery of fluorescent lights, the faderator subjects photographs to a lifetime's daylight. In just a matter of hours, photographs are artificially aged by up to 75 years. A computer then compares their color balance against a control chart to measure fade resistance. This batch of ink has passed the test. Ink is the cartridge's only moving part. It's pumped through tiny nozzles like these. Each cartridge has about 400 of them, set into a plate the size of a postage stamp. Like a micro machine gun, each nozzle pumps out 36,000 droplets a second. It happens so fast, it can only be measured in microseconds.
1 microsecond is a lifetime.
They call him Mr. Bubble. His job is to boil tiny drops of water inside the cartridge firing chamber. The aim, to monitor print velocity. At 2 microseconds, the ink moves in a flash.
To give you an example of how fast these things occur, a beam of light from this flashlight, when I flash the switch on, it goes 1,000 feet in 1 microsecond. So, if I aim it out the window,
1/1,000,000th of a second after I turn the light on, the head end of that beam of light is 1,000 feet away from us.
It's as hot as the sun. It explodes thousands of times a second, and you could just be sitting right beside it. More secrets from inside your computer printer next on How Do They Do It? You're looking at a mind-blowing cosmic event. Inside this printer cartridge, an electrical resistor fires bursts of energy so intense they're 7 times hotter than the sun. The heat vaporizes the ink and pushes it through the nozzle. But relax, the thermal reaction is impossibly brief, just 2/1,000,000ths of a second. You and your computer are safe from meltdown. At this micro scale, the slightest contamination could cause a cartridge engineer's worst nightmare: nozzle blockage. Here at the Droplet Break-Off Observation System, or DBOS, technician Jeffrey Langford reveals what a tiny speck of dust on the nozzle plate does to the ink flow. It isn't pretty. The ink gets blocked. The cartridge can't fire. And that's why the ink is made here. They call it the clean room, a place completely devoid of everyday contamination. No dust, no dirt, not even a speck of dandruff. It's one of the cleanest environments on Earth.
This is a class 10 clean room, which means that there are 10 particles in every cubic foot of air.
Besides ink, the clean room is also where the nozzle plates and firing chambers are made. It's a high-tech micro-engineering operation. But when you're dressed like an astronaut, how do you recognize your fellow workers? Jeremy Donaldson gives us some tips.
After a couple years of walking up to someone and saying, "And you are," you start to pick up on the visual clues of the eyes and just the way someone's shaped and then how they carry themselves.
Back in the main plant, it's the end of the shift, but the cartridge faces one final hurdle. Forget the faderator. This man is a cartridge killer. His job, to get cartridges printing in the hottest, most humid environments imaginable. This is a climate-controlled test chamber. If it works here, it'll work anywhere.
We emulate different printing conditions. So this is a 35 Celsius with 20% humidity. So as an example, maybe printing in Phoenix, Arizona.
And when they're through baking the cartridges, they put them on a tower and drop them.
I drop things, and I enjoy dropping things. It's a great job.
So, next time you hit print, think for a moment about the miracle of engineering under the hood of your computer printer. And watch out for that thermal reaction. It's the closest any of us will ever get to a cosmic nuclear explosion. Thankfully. Behind the ordinary things that surround us in our daily lives are miraculous advances in engineering which we rarely get to see. Ingenious solutions to problems most of us never knew existed. Since this program began, the world's factories have produced around 30,000 fireworks, assembled 4,000 plasma screen televisions, forged 10,000 tons of rail track, made 150,000 ink cartridges, and ground up 57,000 tons of metal for recycling. Even the most ordinary objects often have extraordinary stories to tell. We only have to watch and listen. Behind the ordinary objects which surround us in our day-to-day lives lies something extraordinary. Incredible stories of ingenious solutions to problems most of us never knew existed. So, what mysteries are concealed in everyday things we take for granted? Salt, running shoes, cargo ships, the wristwatch, and wind turbines. 5 ordinary things, 5 extraordinary stories, now revealed as we go behind the scenes, inside the machines to find out, how do they do it? We need it to live. We eat it every day. But where does salt come from? It's midday, but you wouldn't guess it because you're in an underground city. It has its own houses and shops, its own power supply, and a road system large enough for a small town. This subterranean metropolis even has its own petrol stations. The city, of course, is no city at all, but a vast salt mine buried deep beneath the plains of Ontario, Canada. This is the Sifto Salt Works. The plant churns out a staggering 25,000 tons of salt a day. These forklift drivers never stop. Demand is huge, and for good reason. We need salt every day just to survive. Our bodies must carry 250 grams of it to help maintain our blood supply. But salt, which is made up of two basic chemicals, sodium and chlorine, also has a vast number of commercial applications. Indeed, salt appears in over 14,000 different products. Everything from paper to plastic, from cosmetics to chicken feed. And of course, in the brutal Canadian winters, salt stops ice forming on the roads. The most common source of this miracle crystal is a 400 million year old mineral known as rock salt. Thankfully, rock salt is plentiful, but to get it means going a long way down. At 600 meters underground, Goodrich is the deepest salt mine in the world. That's like Toronto's world-famous CN Tower pointing downwards. But Goodrich isn't just the deepest, it's also the biggest. These cavernous streets are the result of the way they dig the mine. It's known as the room and pillar method. As the salt is dug out, giant pillars of rock are left in place to support the roof. With such massive supports, tunnel collapse is pretty unlikely, but smaller rock falls are still a problem, so the miners deploy this. It's a metal dinosaur, and it's the biggest machine in the mine. It's called the descaler. Its job, to scrape away every gram of loose rock and debris until it's safe for mining to proceed. Five kilometers on, deeper into the mine, the ceiling drops to just 3.5 meters. Things are about to get tight. We're approaching the sharp end of the mining operation. It's called the cutter, a kind of giant mobile chainsaw. The cutter slices 3.5 meters into solid rock. The aim, to loosen a huge slab of salt and make it ready for blasting. Charges are laid. The area cleared. The excavators move in to push blasted fragments of rock towards what looks like a hungry hole in the ground. It is, in fact, the upper level of this giant juggernaut, a monster rock crusher. It could be a scene from Aliens, or perhaps Total Recall. The crusher mashes big lumps into smaller bite-sized chunks. It resembles moon rock. It's actually salt. Once crushed, the salt heads off into the gloom along an incredible 7 kilometers of conveyor on a journey that will take it through more stages of crushing and sifting, and eventually to the surface. This salt is now ready for dispatch, but it's industrial, far too coarse for human consumption. To get table salt, Sifto uses a different process altogether. Instead of sending people underground, Sifto sends water. These wells pump a high-pressure jet down 600 meters. The water hits the salt layer and comes back up to the surface as brine.
Yeah, it's very small and not much going on that you can see, but it is one of the most important parts of the plant. Without the brine wells, we really have no product. We have no raw material.
The brine ends up here in a place called the vacuum evaporation plant. It's a high-tech name for a relatively simple procedure. The brine passes through a series of huge vats, each one holding 20,000 litres, where it gets super steam clean under vacuum pressure. Eventually, the salt ends up here, a massive rotary dryer. The temperature is phenomenal, above 40 degrees centigrade. The dryer tumbles the salt until it turns from a gunk-like sludge into fine white powder, ready for the table. It's the end of the day and the end of another shift, but the machines carry on working deep underground. In the past 24 hours, Sifto has extracted another 25,000 tons of salt from its gigantic underground megalopolis. Five ordinary objects, 5 extraordinary stories. Coming up, they're cool, they're functional, they're worn by millions, yet they're also the product of space-age technology. The secrets behind running shoes next on How Do They Do It? Running shoes have got to be good. The average person takes 10,000 steps a day, which is almost 7 kilometers, depending on your stride. In your whole life, you can expect to have walked the equivalent of 4 times around the planet. During a marathon, runners will take 30,000 steps, each one creating a force of up to 4 times their body weight. Running shoes don't just reduce shock and impact. They're designed to prevent injury, improve balance, and can help you run faster, for longer. So when it comes to putting science into sports footwear, how do they do it? Japanese company ASICS are at the forefront of running shoe R&D. They produce 20 million pairs a year.
This part is carved too much. It needs to be filled in here.
Their research institute of sports science in Kobe is at the cutting edge of running shoe technology. Here, scientists and athletes work together to learn how biomechanics can be translated into the manufacture of a shoe. And their leading scientist is Dr. Tsuyoshi Nishiwaki, or Wacky to his friends.
This is the first running shoe the company made about 50 years ago, and it only had 5 parts. These are the current shoes we're making. They consist of about 50 different parts.
Many of the features in sports shoes today are the direct result of his research. Wacky believes to understand the design of a running shoe, you first have to understand the way you run, and every single step has 5 distinct phases. A special pad on the insole of a sports shoe shows the pressure at different stages. By measuring the changes in pressure, Wacky attempts to deduce how to get the best performance out of a running foot. It's called motion guidance.
Motion guidance line is very, very important for designing the running shoes. Based on this line's position and the direction, we designed the reinforcement direction and groove direction, increasing the gripping property.
Studying how the foot works is vital for developing sports shoe designs. Yet the mass production of those designs takes place not in Kobe, but hundreds of kilometers away. It's midday in the Chinese city of Dongguan, and the shifts are changing for the 5,000 workers at the Yueyan factory. The making of a running shoe is split into 3 sections: the rubber sole, the midsole, and the shoe's fabric upper. The perfect sole starts with rubber. The amazing thing about rubber is how versatile it is. One block can be turned into 1 million products. What's important on the sole of the sports shoe is grip, and getting the right gripping property is like cooking. These guys are, in effect, rubber chefs. Welcome to the ingredients cupboard. In this lab are different chemical compounds, each carefully weighed and added to the rubber. These give it its different qualities. Everything is thrown into a mixing machine, where it's cooked and kneaded like dough. Giant rolling pins flatten out the rubber dough before it's stretched into long, thin sections. This gunge must now be turned into a running shoe. The rubber is placed carefully into metal molds, like sandwich toasters, and pushed into ovens to melt them into shape. It's hot work. Each section of rubber is built up through a series of molds to make a finished composite sole. Finally, the rubber sole emerges with all its various textures and patterns. It might seem like a work of high fashion, but there's real science in this sole. Back in the research lab in Kobe. Today, Wacky's looking at heels. The heel takes the most impact when running. It's the foot's natural shock absorber. That's why there's so much skin and tissue there. But with 4 times the body weight of the runner pounding on the heel, that's a lot of potential damage. So, what is Wacky's solution?
We inserted this intricately designed gel at this position and at this position. These gels absorb high ground reaction force in running.
The gel is so good at absorbing and dispersing energy from impact, they proudly said it could even prevent an egg breaking from 6 meters. So we put them to the test. The special gel disperses the energy of the impact outwards rather than straight down, spreading the force, not compacting it.
Okay, it's not broken.
And just to prove it's not broken, back in China, on the assembly line, this gel is glued in between 2 parts of the midsole. The completed midsole has all the gels, cushioning and support elements. It just needs the finishing touch, the molded rubber sole. All that's left is for the midsole to be checked and cleaned. Now the underside of the running shoe is complete. Back in Japan, Wacky is looking at the way the foot moves and how that affects the upper section of the running shoe. As it lifts off the ground, the foot is at its most deformed. All the straining is on the joints around the toes. This uneven strain distribution causes the running shoe to scrunch up behind the toes. What Wacky has done is apply a stretchable fabric in between.
We inserted new stretching materials on here. We called it biomorphic fitting systems. These stretching materials interrupted the strain continuity from here to here. Okay.
Wacky's designs all need to function in extreme conditions. This special climate-controlled chamber generates temperatures ranging from 60 degrees to minus 15 degrees centigrade. Right now, it's minus 15. This guy's running in the Arctic. The climate chamber also monitors another factor when running: sweat. There are 250,000 sweat glands in the feet, more than any other part of the body. They excrete up to half a pint of moisture a day. The foot needs to breathe. The solution is multi-layered gas-permeable fabric. The fabrics are concentrated on the top section of the shoe called the upper, which is the final part of the running shoes manufacture. Layering fabrics is part of the secret of breathability. The uppers are wrapped around thousands of plastic feet, called lasts. An insole is hammered onto the bottom. Each batch of lasts is for a particular shoe size. One of these has your number on it.
It's not easy to make a shoe. By the time it's finished, it has gone through 300 pairs of hands.
The shoe is cooked over a grill and clamped around the last. The heat softens the rubber, which is then squeezed into a finished shape. Now it may look like a running shoe, but no one's going running just yet. Not without a sole. Two conveyors bring the sole and the upper part to be glued together. Finally, the laces are tied. The running shoes are cleaned and boxed, ready to be sent around the world to where size 10 feet need them. The appetite for running shoes is voracious. US sales alone exceed $14 billion. In China, 300 pairs of hands have put together 50 separate parts to produce a marvel of engineering. Back in Japan, planning the next running shoe has already begun. Five ordinary objects, 5 extraordinary stories. Coming up, they're bigger than a city block, monstrous creations of iron and steel, yet they build them just like Lego. The secrets behind ship construction, next on How Do They Do It? 90% of world trade is moved by ship. As demand for products increases, ships need to be bigger and stronger to accommodate the growing volumes of cargo. In Korea, they've taken shipbuilding into the 21st century. So when it comes to putting together a modern-day super cargo ship, how do they do it? On the southern tip of South Korea is the town of Okpo. This is where the world's largest industrial vessels are produced. And the way they do it is incredible. Traditionally, ships were made from the bottom up, but not here. At this shipyard, a ship is put together more like Lego. 85 separate blocks, each one weighing around 400 tons, are joined together one at a time. This is Lego for giants. The workers at the Daewoo Shipbuilding and Marine Engineering Shipyard are deservedly proud of the 40 ships they make each year, because these are the Trojans of the sea. And they don't take their work lightly. Every day starts with morning exercises. The blocks look like they've been cut straight through the middle with a saw, and in a way they have. But not by hand, by computer. Every new design of ship is broken down into precise and detailed three-dimensional sections, like blueprints. It's called cyber fabrication, and it makes finished individual 50-meter blocks, ready to go. All you have to do is put them all together. But what happens if one steel sheet is cut a centimetre too wide or welded in slightly the wrong position, or fitted together just out of place. The finished block will not fit the jigsaw, and that costs, well, a ship. So how do they make sure every part of the process achieves the accuracy needed for this system to work? Introducing the plasma cutters, the tailors of steel. The pattern on each plate is transmitted directly from the computer. It's mapped out on the plate first, then cut using a device a bit like a welding torch. The different sections are then given an individual number and sent on their way. Working to an exact blueprint means this is shipbuilding by numbers. In the assembly shop, if the cyber fabrication system is working, all the cut steel plates should slot exactly into place. Still, there is a little coaxing to be done. The steel slabs need to be winched tightly into position, then locked using hydraulic clamps. As they make their way down the assembly line, each new section is added piece by piece, resulting in a massive 50-meter finished block. Moving the blocks into position is down to the keen eye of the workers. Making sure they stay in position is down to the welders.
All products like oil, gas and cars are carried by ships. To make one ship takes 1 million sections of steel, all put together by welding.
The quality of welding is crucial to building a modern vessel. If a breach occurred and a weld was not watertight, it could potentially sink the ship. However, there are some places that even the tiniest of welders cannot reach. Only one thing is up to the job: a robot. These are automatic welding robots. They can squeeze into the smallest spaces. And they get commands from the main computer. Over 1,000 control programs translate information about type and depth of weld. As the blocks are finally assembled, man and machine work side by side. But once it's finished, how do you move a 50-meter, 400-ton block to the dockside? These transporters may look like something out of Thunderbirds, but they're the cool solution to the problem of carrying the blocks around the shipyard. Each transporter has its own safety warden cycling ahead of it to keep traffic out of the way. This method of putting all the blocks together at once is only possible with a combination of precise measurement, designed through cyber fabrication, and the world's largest Goliath crane. At over 120 meters high and 150 meters wide, it can lift weights of up to 600 tons. It's so big that just the letters on the top are the length of a bus. Its job is to lift the assembled blocks and drop them precisely into position onto any one of the 5 ships that are being made in the dock. To get there, this lumbering giant moves 300 meters along a rail track, shifting other cranes out of its way as it goes. Now the block is ready to just slot into place. However, here is the moment of reckoning. Will it fit? Have all the parts of this cyber-fabricated ship been made accurately enough? And how do they fit it together without leaving any gaps? Measuring the position and specific size of the ready-made block is done using special 3D equipment. This identifies 3 coordinates on an X, Y, and Z axis by locating targets placed on the block. These coordinates are fed into the computer and compared to the cyber design. The tiniest error in measurement must be corrected and the block pulled into position, even if it's just a matter of millimeters. The final gaps between the blocks are sealed by welders. Finding out whether the ship is actually watertight, we'll have to wait for the launch. It will take 3 years to put all 85 blocks together. Only then will this ship be named, launched, and sent on its way. Then another single block will take its place, and the whole process starts again. 5 ordinary objects, 5 extraordinary stories. Coming up, they're miniature marvels of engineering, yet to work they rely on a rock that dates back to the dawn of time. The secrets behind wristwatches, next on How Do They Do It? Since the dawn of civilization, we have used the measurement of time to order our world. With our finely tuned modern lives, accurate timekeeping has never been more important. But the majority of us take the most common form of timekeeping technology for granted. The story of the wristwatch is a tale of 3 seemingly impossible hurdles. Energy, how to produce enough power for the watch to work. Size, how to fit this into this. And accuracy, how to measure time itself. So, how do they do it? It turns out the best source of super accurate timekeeping is right beneath our feet. Quartz. Quartz is the secret ingredient of modern timekeeping. And incredibly, it's one of the most common minerals on the planet. It makes up around 12% of the Earth's crust and is found on meteorites and moon rock. It is everywhere. However, before it can be used in a watch, it has to be mined. This is the SciTech Open Cast Quarry, north of Quebec City in Canada. It processes 200,000 tons of quartzite every year. The question is, how can a common rock tell the time? Incredibly, quartz has a hidden quality that only reveals itself when under pressure. It vibrates. When compressed, it creates an electrical charge that makes it continuously oscillate, 32,000 times a second. To make use of quartz in timekeeping, it's placed inside a tiny metal vacuum called an oscillator, each one the size of an ant. The quartz can then be linked to a circuit board, which is programmed to count the 32,000 pulses, then return to 0. Which means the constant vibrations made by the quartz are translated into electronic pulses, each one a second long. And that's how a rock becomes a clock. At Seiko Epson Shiojiri factory in Japan, the oscillator is just one of 250 tiny parts that they have to fit inside each of the watches they make. The workers who assemble these parts have to pass through a special dust-free wind tunnel. One single speck of dust could ruin their day. The assembly process involves both humans and machines. And the same interaction of man and machine is how Seiko Epson have overcome one of the greatest challenges in watchmaking. How to create a watch that generates its own electricity. What they've done is to use the motion of the body to power a kinetic watch. The kinetic watch captures the energy from the natural movements of the wearer's arm, amplifies it, stores it, and uses it to power the timekeeping mechanism. Seiko Epson has essentially reduced a power plant to the size of a thumbnail. Unlike other watches, the designers of the kinetic watch take positive advantage of the fact that it's worn on the wrist.
The kinetic watch is unique because it only needs arm movement for power.
So how have they done it? An oscillating wheel turns each time the arm moves. This movement is increased 100 times through 3 cogs and eventually reaches one of the smallest components in the watch, the rotor. This is the heart of the kinetic watch. It's just 1/4 millimeter in diameter. To produce the 1 volt of energy needed to power all the parts inside the mechanism, the rotor spins at a speed 5 times faster than a Formula 1 racing car engine. And that's how the simple movement of the arm creates energy. But what's clever about the kinetic watch is that it also saves energy, especially the part that needs more power than any other, the hands. They only need power when they move, and not between the ticks. In theory, this watch could be worn by one person from the moment he or she is born, and never stop. It's an awesome thought. But for this to happen, the watch needs to be sealed for life, and never opened or exposed to the atmosphere. To make sure it stays sealed, it goes through a series of rigorous tests. In a high-pressure cylinder, the watches have to withstand deep-sea depths. Then, they're submerged in water to check for leaks. If water is present, drying the watch on a hot plate will reveal condensation on the glass. These watches have passed the test. Now the kinetic watch can last a lifetime and join the rest of the world's watches to mark and maintain the daily rhythms of the human race. Five ordinary objects, 5 extraordinary stories. Coming up, it's a novel form of power supply and its biggest enemy could sit on your fingertip. The secrets behind wind turbines, next on How Do They Do It? They stand like giant sentinels against the sky. The only apparent movement, massive blades silently spinning. Look around, and there are dozens of them. Look again, and there are hundreds. Look again, and the effect is hypnotic. The spinning blades lazily drifting in and out of synchronized movement. But how does a wind turbine work? The first ingredient, of course, is wind, and plenty of it. This is the Tehachapi Valley in Southern California. The geography of this valley makes it one of America's windiest spots. Tehachapi lies at the edge of the Mojave Desert. As hot air rises from the baking ground, cooler air is drawn from the Pacific coast, some 200 kilometers away, and funneled up the valley. Weathermen call it convection, and it's why Tehachapi is surrounded by more than 5,000 wind turbines. Turbine engineer Michael Burns works for Oak Ridge Energy Systems, one of the dozen or so wind farms that operate in Tehachapi. It's Burns' job to keep the turbines turning. And the biggest challenge he faces is one you might not expect: bugs.
The bugs deposit on the blade, on the leading edge, and when the air is supposed to follow the contour of the blade, instead of following it and staying attached, it's like it hits a speed bump, so it comes around and goes like this away from the blade, which causes it to lose lift, which is kilowatts. You could turn a 750 kilowatt turbine into a 400 kilowatt turbine, just from bugs on the blades.
Bugs can seriously hamper electricity production. In the Oak Ridge Energy Systems Control Center, staff have come up with a neat solution. At the press of a button, a computer triggers this. It's a kind of giant car wash, and it's designed to keep the blades clean and bug-free. Clean of bugs, the blades can rotate up to 50 times a minute. Their job? To convert the forward movement of the wind into a circular motion, and then translate that motion to the business end of the turbine, the generator. The generator is housed in a compartment called a nacelle. The only problem, it's around 60 meters off the ground. And the only way to get to it is straight up. It may seem a daunting prospect, but to Burns, it's all part of the job. the top, the space inside the nacelle is cramped. But the views across the Tehachapi Valley are spectacular. At last, the business end of the turbine is revealed.
Okay. Main shaft, gearbox, the generator. So that lift is converted into horsepower, which is then converted into energy.
The raw current runs through these massive cables all the way down to ground level. At the tower's base, the cables link to a transformer. Here's where the second bit of magic occurs. The transformer bounces the electricity between two magnets of different strengths. The result is a step up in the current from 25,000 to an awesome 450,000 volts.
When the wind is up high enough and all the turbines are producing what they're supposed to, this part by itself could supply 34,000 volts.
To provide electricity for even a small windy town like Tehachapi takes an awful lot of windmills. But wind turbine technology is still in its infancy, and engineers like Michael Burns are determined to make it work. The world spins through another day, another night. Industry never sleeps. Somewhere, somehow, someone is at work, designing, producing, distributing. Since this program began, worldwide we have mined over 25,000 tons of salt. 143,000 pairs of running shoes have hit the world's streets. And with a fair gust, a giant windmill has managed to power 11 million 100-watt light bulbs. The rock on your wrist has made your watch tick around 3,000 seconds. And another 100 tons of steel have been forged into a chunk of giant ship. Even the most ordinary objects often have an extraordinary story to tell. We only have to watch and listen. Behind the ordinary objects which surround us in our day-to-day lives lies something extraordinary. Incredible stories of ingenious solutions to problems most of us never knew existed. So, what mysteries are concealed in everyday things we take for granted? Tires, the excavator, ports, newspapers, and the contact lens. 5 ordinary things, 5 extraordinary stories, now revealed as we go behind the scenes, inside the machines to find out how do they do it. The only time we give it a moment's thought is when it's flat. And yet the rubber tyre has played a massive part in shaping the modern world. We travel more today than ever before. And to help us move with ease and speed, we've come to rely on this deceptively brilliant invention, the tyre. Here at the Pirelli test track, just outside Milan, Italy, technicians test high-end tyres designed specifically for the fastest road cars in the world. Tyres have one heck of a job. They must be durable, able to run for up to 128,000 kilometers apiece. They must grip the road at all speeds and in all weather. They must support a heavy load, but give a comfortable ride. How they manage this is a fantastic story of chemistry and engineering. The action begins here at Pirelli's high-tech plant, with some state-of-the-art industrial robots and some ingenious smart technology. The tyre consists of various elements. The body begins life as a dual-layered rubber strip called the ply. Ply is made of rubber mixed with a synthetic fibre, more often associated with home furnishing, rayon. The rayon fabric is there to stop the rubber from tearing apart under pressure. After the ply come the tyre sidewalls. These have to absorb the weight of a 2-ton car. So to do their job, the sidewalls must have something more than just rubber. That other component is steel. Here, a robot is inserting steel belts to the inner part of the sidewalls. On cue, the smart robots bring together the tyre ply with the sidewalls. They work with incredible precision. The match is invariably perfect. the join appears seamless. Once the two sections have come together, another thick layer of rubber is rolled on, completing what they know in the trade as a green tyre. Green tyres look pretty much like the tyres on your car, but they're still missing a crucial feature: tread. The design of tread is essential to the success of a tyre, but there's something rather surprising which tyre manufacturers look for in a tread. It has to make the right noise. In particular, it shouldn't make too much noise. In Pirelli's R&D lab, this tyre is about to face a range of audio tests, which will determine whether it is fit for the open road. If you listen carefully, you'll hear what the engineers are looking for. Nothing. The sweet sound of silence. At Pirelli, this is a serious business. The chamber is very heavily soundproofed. The tyre must meet exacting acoustic standards.
If the technicians feel the carcass is too noisy, then we intervene on the tyre to lower the noise emissions.
The tyre is placed on a treadmill, which simulates driving along a highway. Highly sensitive microphones are placed around the tyre and connected to a computer, where the audio signals are converted into sound waves. For this tyre, it's so far so good. But now, it is really going to be put through its paces. It's about to be pushed to the limits in Formula One racing conditions. Our modern lives depend on trucks, buses, cars and planes. And all these depend on tyres. Modern car tyres are expected to last a staggering 128,000 kilometres and still be safe. So, how do they do it? This is a normal road tyre, but it's about to be treated as if it were in a Formula One race. Once the tyre is locked firmly into place, the technicians punch in the weight of an average town car. Then, the speed begins to increase. The idea is to see how the tyre performs under extreme circumstances. With the naked eye, it would be impossible to see what is happening to the tyre, even at slower speeds. So, Pirelli technicians have come up with an ingenious solution. At the flick of a switch, the speed chamber is flooded with stroboscopic light. When set to the correct frequency, the flickering light makes it look as if the tyre has stopped moving. This allows the operators to inspect the tyre as it's turning. But today, the team is testing a new kind of tyre and have decided to push it especially hard. The speed reaches a nosebleed-inducing 350 kilometers per hour. That's faster than a jumbo jet's takeoff speed. Incredibly, the tyre remains intact. It's passed with flying colours. Once a new tread is approved, it must be applied to another generation of tyres. That requires a spot of baking. This is a curing oven. Its robotic brain calls out for another half-finished green tyre. Each oven contains a large inflatable bladder. As the bladder expands, it'll push the tyre against the mould. Steam will then be pumped into the bladder, and the tyre is cooked at 135 degrees centigrade.
This is the green tyre is pushed into the mould and the tread branded on.
In just 12 minutes, the tyre will be complete. As the machine opens, the tyre gently falls out of its mould. Another tyre, ready for another 128,000 kilometres. Behind the ordinary objects we take for granted lie some extraordinary stories. Coming up, the excavator, the essential tool for building everything from roads and tunnels to bridges and buildings. Next, on How Do They Do It? As we get more and more ambitious about the cities we want to construct, the tools we need must be more powerful, lift heavier loads, and break harder materials. Most machines excel at one task. But there's one which can turn its massive hydraulic hand to almost any major construction job. The excavator. Commonly portrayed as mere diggers, these monsters do much more than dig. In the trade, they're called tool carriers, which means one day it's a crane, the next it's wielding a tree-slicing wheel, and the next it's smashing rocks. The excavator is the #1 heavy-duty, all-rounder building power tool. It is the decathlete of construction. But how do they pick up such gargantuan loads? How come they don't topple over? And why don't their arms just snap off under such weights? How do they do it? The answer can be found at Volvo's excavator factory in Changwon, Korea. The company turns out 16,000 excavators from their factories worldwide every year, each one taking 5.5 days to make. Here in Korea, they make the big ones. At 70 tons, they are the Goliaths. But don't be fooled, these heavy-duty monsters are more human than you might think. The design of an excavator has many similarities to the human body, and they can, in their way, be just as graceful and delicate. The body of the excavator can be compared to a human torso. The undercarriage to the legs, the arm and boom to a muscle-bound human arm, and the attachments to the hand and fingers. When loading or lifting, a stress will move from the bucket to the arm to the boom and undercarriage in the blink of an eye. And when heavy loads are put on the structure, it's designed to deform like a body to absorb that stress. And of course, they have to be able to dance to the tune of the operator. But the most human characteristic is not visible when you watch an excavator at work. An excavator has a big heart, a massive hydraulic pump which pushes oil, like blood, around the arteries of the machine. And the nerve center of the excavator is the main control valve, otherwise known as the MCV. The MCV directs the hydraulic oil from the pump to specific areas, to the boom arm, to the bucket, the tracks. The secret of the excavator's extraordinary ability is the way the MCV decides how much oil to let through to its different parts. The more oil, the bigger the movement. With hydraulics, it's possible for a small amount of effort at one end to be translated into lifting a monster weight at the other. Each hole in the MCV is drilled with remarkable precision. The tiniest difference in size will affect the flow of oil, and therefore the hydraulics. With the help of an endoscope, the MCV is cleared of any minute dirt particles that could delay the machine's reaction to the operator. Spools are inserted into all the holes, each one controlling the amount of oil flowing to a different part of the machine. By moving the joysticks in the cab, the driver sends a signal to a computer which acts like a nerve system, deciding how much pressure needs to be applied where in order to fulfill a command. And the accuracy and delicacy is quite incredible. Putting together all the different parts happens on the 110-metre-long assembly line. It takes 150 highly skilled workers to make an excavator. The boom arm needs to be very strong, but if they're too heavy, then they'll be slow and cumbersome. The solution is surprising. At first glance, it may look solid, but this excavator's arm is actually a hollow box structure. This makes it light and manoeuvrable. The way the arm can be both hollow and strong is down to some very clever robots. The precision with which these robots can weld means they can produce slower and deeper welds. The deeper the weld, the stronger the join. These guys can finish off 20 arms in a day, getting through 3 tons of welding material. And they don't make mistakes because they're programmed to self-diagnose and mend themselves. This is artificially intelligent welding. After the parts have been made, comes the assembly. First, the union of the upper structure to the undercarriage, romantically called the marriage. But before the vows can be completed, there's a little preparation to do. All the cogs must be greased up. On the chassis is a big wheel which has other cogs attached to it. The superstructure has a mini cog on its underside which attaches to this wheel. And this joint enables it to turn around 360 degrees. It's a simple idea that makes the excavator super versatile. A single crane is used to lift and carefully position the cab onto the deck of the superstructure. Then they're screwed together using just 5 bolts. Once the 5th bolt is in, the marriage ceremony is complete. The next step on the assembly line is attaching the arm and all the hydraulics back to the main control valve. Then the first test is to make sure the hydraulics are working. But one of the big secrets to how an excavator works can now be revealed. It may look light enough when it's being lifted by crane, but these full metal jackets weigh up to 12 tons. On the front and back of the excavator sit these massively heavy cast iron counterweights. They need to be heavy because the jobs an excavator can do is directly related to its own weight. Excavators can lift 30% of their weight. They can break objects with a force of 60% of their weight, and the buckets can carry 10% of the machine weight in one go. So the heavier, the better. And carrying one on the front and one on the back means they can change them to suit the job. These 70-ton excavators may be powerful, and they may be versatile, but they're no racing cars. In fact, to get around, they need their own fleet of taxis, or rather, super taxis. The excavators are loaded onto the back of trucks, destined for various locations. Anywhere in the world where there's heavy construction or destruction. 5 ordinary objects, 5 extraordinary stories. Coming up, the newspaper. Next, on How Do They Do It? It's a familiar sight, a busy kiosk at rush hour on a crowded city street. Hand over your change, buy a paper. But behind the news bought by countless millions on the daily commute, there's another remarkable story. Increasingly, the news you read is printed on this. Rubbish. Recycled newspapers and magazines. The triumphs and heartaches of 1 million people bought, read and consigned to the garbage heap. So how do they turn yesterday's news into tomorrow's front page? Welcome to Aylesford Newsprint, 50 miles southeast of London. This 100-acre site is home to the biggest paper recycling plant in Europe. It's dedicated to making one thing: newsprint. Newsprint is what they call the raw paper that newspapers are printed on, and the world consumes a staggering 38 million tons of it every year. Aylesford alone generates nearly 500,000 tons of newsprint a year. The operation is, quite simply, enormous. This is where tomorrow's news begins. The recovered paper store consists of 3 giant bays. Together, they're the size of a shopping mall. At the rate of 1 every 10 minutes, trucks move in and out to unload up to 18 tons of waste paper each. As the week goes on, the room is gradually filled to the rafters with waste paper.
In this one bay, there's approximately 3,000 tons of newspapers and magazines.
Most of this waste has already been recycled, who knows how many times. But mixed in with the paper are rogue items that threaten the entire process. Banks of magnets and mesh barriers make sure they don't get through.
Plastics, tins, wood, metal, staples that hold magazines together, CD-ROM, I just saw one drop down there. Whatever comes in the waste we cannot convert to paper.
But how does all this scrumpled rubbish get turned into clean, crisp white paper? Get ready for the biggest mashing machine in the world. Recycling newspapers involves some of the hottest, wettest and most extreme machine environments in modern industry. First stop, these giant cylinders. They churn the paper in boiling water until it becomes a broken, sodden mass. The aim, to break down the fibres that knit paper together. The end result is this: hot, sludgy pulp. When it's fully pulped, the sludge is pumped next door to spend a little time in a room the size of a football field. It's known as the fibre preparation plant. The purpose of all this machinery is to wash the pulp in a high-strength soap to remove the ink and glue. This is the pulp's final destination, a gigantic paper maker, 90 metres long and 30 metres high. This monster machine costs over £100 million to build, and it's the biggest of its kind in the world.
The machine operates at just over 60 mile an hour or 1680 metres a minute in paper-making terms.
Before the pulp enters the paper maker, it passes through a kind of giant washing machine. 100 tons of water agitate every ton of pulp to help knit the paper fibres back together. At this point, the pulp is still more water than paper. The next stage is to drain and steam the knitted pulp and pass it through giant rollers. In 24 hours, the roller produces enough paper to stretch from London to Athens, a distance of over 2,400 kilometres. Shipping the finished reels of newsprint out is as big a job as shipping the waste paper in. Straight into the back of waiting trucks. The plain paper reels in the back of this truck are about to get turned into tomorrow's news. But how do they do it? News International is one of Britain's biggest printing operations. It produces 4 titles and up to 31 million newspapers and magazines a week. These guys are called Automatic Guided Vehicles, or AGVs for short. Think of them as R2-D2's great-great-granddaddy. They move around a pre-programmed route, delivering newsprint to the insatiable printing presses. The newsprint comes into docking stations or wheel stands directly beneath the press itself. On the leading edge of the reel, there's a connector called a kite. The operator hooks the kite to a chain that will pull the reel right into the press through a forest of rollers that wind it into a complex pattern called the web. The operation looks simple. It isn't. Getting the web's tension right is crucial.
If it's too slack, what you'll find is the web will wander and will cause us anything like a jam. We could have jam up or a web break, or if, again, the paper's too tight, it just snaps straight out on us. So we need to keep it balanced.
In another part of the building, the noise level is lower, but deadlines are tight and the business is pressured. This is the plate room. Here, the page layouts are formatted in a way the presses can read. The layouts come in as computer files. Giant laser scanners etch a faithful copy of the layouts onto aluminium plates. But here's the catch. For a full-colour newspaper, you need 5 plates for each page. And that means creating an awful lot of plates.
Generally, we make over 4,000 plates a night.
And if the plates were to get mixed up,
it'd be one great big mess.
As the plates are loaded onto the presses, another part of the printer's dark art is revealed. Plates don't print directly onto the page. Instead, they print onto another cylinder, and it's this second cylinder that does the business. As the city gets ready to go to bed, the printers go to work. The presses run at high speed. They get through a 16-kilometre long reel of newsprint every 20 minutes, and that means feeding fresh reels into the presses on the run. So, how do they do it? Like a relay race, as one reel is running out, a second reel is starting to spin. At the last moment, a splicer cuts the outgoing reel and gums it onto the front of the new reel. So fast, you can barely see it. Without so much as a twitch, the presses keep rolling. So far, the presses are printing onto a single roll. But this machine funnels the reel down towards a blade that cuts and folds the page into this, a row of neatly folded newspapers. Each newspaper now finds itself on an intricate switchback called a gripper conveyor. You might think they'd be headed for the dispatch bay, but you'd be wrong. Have you ever wondered how the sports section, the comics, the fashion supplements all get inserted into the main body of the newspaper? It's a job so big and so fast it could never be done by hand. Instead, machines do it with incredible precision. The supplements have been printed and stored on giant 2.5-metre diameter drums. The main newspaper, the so-called live copy, heads along the conveyor towards a machine called an insertion bin. The drum begins unfolding the supplements. At just the right moment, the two meet. A robotic arm literally slides the supplement into the newspaper, so precisely that a particular page number can be chosen as the point of entry. It's a roller coaster ride for newspapers. It's now almost time for the morning edition to hit the streets. The papers are stacked and bundled 25 at a time, loaded into trucks and shipped out. The night's work is almost at an end. Come the morning, and the daily news is in someone's hand. Strange to think that in a few short hours, this newspaper's journey will begin all over again. 5 ordinary objects, 5 extraordinary stories. Every product has taken a journey to where it is either made, sold, or bought. And for most objects in our global economy, at some point, that journey will have been by sea. Coming up, ports. Next, on How Do They Do It? Over 90% of world trade is carried by ships. Cargo shipping is what makes the global modern economy work, but most of us will never see how it's done. Hong Kong is the busiest port in the world. It handles a staggering 22 million heavy steel containers a year. Exports must be unloaded from lorries and trains, stored and then loaded onto the correct ships. Imports must do the same in reverse. It's like baggage handling on a nightmare scale with really heavy bags. So, how do they do it? Hong Kong is small. 100 years ago, it was a humble fishing port. Space is extremely limited, so it's had to grow upwards. This lack of space is a huge problem for the port. Freight is valuable, and handling and keeping track of containers poses a huge challenge. The port is divided up into separate terminals. The largest is Hong Kong's International Terminal, or HIT. 1,500 workers and a high-tech computer system means that a massive cargo ship can be unloaded and loaded in only 6 hours. It's a tough job at the best of times. It's even tougher when there's a typhoon brewing. A direct hit to the port would throw the containers around like empty garbage cans. But the greater risk is to a ship. It's much safer for a ship to ride out a storm at sea than be chained to a dockside. So it's a race against the weather to get unloaded and back to the relative safety of the open seas. One ship can have anything up to 10,000 containers on board. The captain first has to communicate where each of the containers are kept in the hull.
Dominion, do you read me? Over.
Then it's down to the HIT operators to get the right ones out and move them into the right parking spot in the yard. Unloading the ship involves the expertise of guys like this. Siu Fan is on his way to work. Upwards. Vertigo sufferers need not apply. Siu Fan spent 15 years as a rookie on the smaller gantry cranes in the port. Now, he operates the largest crane in Hong Kong. Siu Fan has to sit 40 meters above the ground. Moving his crane along rails, he positions it beside a ship. Then he has to haul each 30-ton container off the back of the ship and place it precisely onto a truck chassis. The smallest mistake can be very expensive and often highly dangerous. This massive crane uses an incredible piece of lifting equipment called a spreader. It's called a spreader because it can spread or expand to carry two 20-foot-long 30-ton containers at once. It can reach into a hold 15 meters below sea level and lift up to 40 meters above the deck. Siu Fan maneuvers his cabin at a speed of 3 meters a second, hovering over the ship's containers. The accuracy required to pick up and drop each container into its exact position comes down to Siu Fan's eagle eyes and his rock-steady nerves. The small holes on top of the container are the target Siu Fan's aiming for. To give him a little help, there's a metal flap, like a flipper, which lowers into position and guides the spreader down. Siu Fan then has to get the small bolts in the corner of the spreader into the holes on the top of the container. Only then will the simple twist and lock mechanism grab hold of the container. Picking it up is one thing, but how does he know where to put it? Back at Hong Kong International Central, every container Siu Fan is lifting off the ship is being logged. The huge mainframe works out the real-time movement of the containers from the ship and allocates places for them in the yard. This information is then sent by pager to the lorry drivers. Yuan Xiu-chung drives truck number MG20. He has to find Siu Fan's crane amongst the 137 other cranes in the yard and position himself directly below it to drop off or pick up a load. Meanwhile, up in his cabin, Siu Fan can see the storm approaching and he still has the rest of the containers to get off the ship and new ones to load. As truck MG20 arrives, it's all down to trust and Siu Fan's expertise to lift the cargo off the truck and onto the ship. Then another must be loaded onto Siu Chung's truck, who's ready to take it on to its pre-designated spot in the yard. Once again, it's bullseye for Siu Fan. 8,000 trucks come and go every day. Some take the containers into mainland China, but Siu Chung has a more difficult task ahead of him. He has to find row 4, aisle 10, for a date with a gantry crane. These cranes can drive to any position around the yard because they're on rubber tyres rather than rail tracks. A gantry crane lifts the container off the back of Siu Chung's truck and stacks it in a precise location worked out by the computer, in amongst the 80,000 other containers here. As Siu Chung goes to pick up his next container, the cycle moves on. Thanks to Siu Fan and Siu Chung, the ship is unloaded and loaded just in the nick of time, and goes on its way before the storm hits. Just another day for the giant baggage handlers who work in the busiest port in the world. Behind the most ordinary objects hide the most extraordinary stories. Coming up, the contact lens, a miniature wonder of engineering that brings the world into focus for 95 million people. Next, on How Do They Do It? The southwest of Ireland. You might think of poetry and music, but these days you should be thinking of white-hot, high-tech industry. This is a state-of-the-art industrial plant. It covers some 250,000 square feet, and it makes the contact lens. 95 million people depend on contact lenses, but why?
The eye is an amazing organ, but if it's not in perfect proportion, light entering the eye is going to be out of focus.
Many people's eyes don't grow in perfect proportion, therefore light doesn't focus on the back of the eye. This results in what optometrists call refractive errors. To correct poor vision, some tool must adjust the focal point, and that means using a lens. Manufacturing a contact lens starts in the lab. These bottles contain the ingredients from which contact lenses are cooked. They're a kind of liquid plastic called acrylic. Acrylic is pretty strong stuff. A little goes a long way.
We get about 25,000 contact lenses from each of these bottles.
The acrylic is distilled and purified and mixed in giant blenders. The process bears a passing resemblance to another traditional Irish pastime.
Outside of the whisky factories, this has got to be one of the biggest stills in Ireland, and it's legal.
At a microscopic level, the acrylic now takes on an extraordinary structure. Its molecules will very quickly join up into long and easily shaped chains called polymers. To provoke this chain reaction, you add heat. Sounds straightforward enough, but there's a catch. The problem lies with the biology of the eye. The cornea is the only part of the human body that has no blood vessels. That means to stay healthy, it needs constant contact with air. Cover it up, and the cornea will fall prey to infection, and that could cause blindness. So, Bausch and Lomb have come up with a range of porous lenses that let air reach the eye. This is the secret behind the durable contact lens, a simple two-part mold. Hundreds of molds are continuously fed into a machine that injects a few drops of liquid acrylic in between the two parts. A casting machine moves the injected molds through a UV scanner that triggers the polymer chain reaction that turns the liquid into a lens. Each mold is individually made to prescription. Curiously, soaking polymer acrylic in water makes it more permeable to oxygen. And if the eye can breathe, the lenses can be worn for longer. Then it's time for a final manual inspection.
We look at each lens on the comparator, and if there is a flaw, after stretching the lens, if the flaw is clearly visible, we take it out and dispose of it.
And that's how you make a contact lens. Since this program began, worldwide more than 100,000 tyres have been made. 4,000 tons of newsprint have been bought and thrown away. 2 million excavators have lifted the equivalent of 80 million tons. Every product imaginable has been moved between the world's ports by 50,000 ships. And 95 million people have put in or taken out their contact lenses. Even the most ordinary objects have an extraordinary story to tell. We only have to watch and listen.